Okay, this is the first video on water and polarity, and we're going to be talking about solutions and water and how water interacts with other water molecules as well as other things that get dissolved in water. So let's dive right into it. And of course, we know that water has a formula of H2O. But if we were to draw the Lewis structure, the Lewis dot structure for water, we'd have our central oxygen, and then we'd have a hydrogen, and then we'd have a hydrogen just like this. Now, we need to put on our valence electrons. Remember those electrons that are available for bonding. Because oxygen is in column 6, what we're going to do is enter in the valence electrons. Again, column 6 is where oxygen lies, so it has 6 valence electrons, or electrons available for bonding, even though we know it has 8 total electrons. So 1, 2, 3, 4, 5, and 6, and those are our valence electrons we've just thrown in there. Hydrogen is in the first column, column 1A, so it has 1 valence electron each, just like that and that. And we're going to go ahead and make a bond between the hydrogen and the oxygen, and the hydrogen and the oxygen, just like this. And what we've just created, if you remember, is we've created a single covalent bond. And a single covalent bond is a bond that occurs when we're sharing electrons to form that octet. Now, oxygen does have an octet, and just to look at it here, we can see that we have, on the oxygen, we have 2, we have 4, we have 6, and we have 8 valence electrons there for just the oxygen, so it definitely does have an octet. And hydrogen is okay with 2 for its octet, so that's what we see happening on the water molecule. Now, that's going to come into play here in a little bit, and so let's continue talking, and then we'll come back to this water molecule. That was just a review there. Okay, so let's scroll down here. Now, here's about 4 definitions that are very, very important for us to know. Definitely jot these down. And the first one is the idea of polarity. And now what polarity means is we have a molecule, even though it's a overall neutral molecule, it's going to have a slight charge. And the reason why it has a slight charge is because we have unequal sharing of electrons. So sometimes these electrons, they're not shared equally among atoms. And remember, an electron is a negative charge. So if we have a molecule with a lot of electrons on one side of it and few electrons on the other side of it, that molecule is going to be a little bit negative where all the electrons are hanging out, because electrons, once again, are negative. Our next definition that we're going to talk about, we're going to put these to use here in a little bit, is the idea of electronegativity. And this is something that we talked about before when we talked about periodic trends. Electronegativity was a trend, if you remember our periodic table, rough little periodic table. As we go down the periodic table, electronegativity decreases in atoms, and as we go to the right, it increases to the halogens. And here's what's happening. Electronegativity is the tendency of an atom to attract electrons, so it's going to pull electrons towards it when it's bonded to a different atom. Okay, so not all atoms will share those electrons equally. They'll pull on the electrons, kind of a little tug of war of electrons, and whoever's the most electronegative will pull the electrons towards it. So let's go back to our water molecule again and see what's going on here. So we have water. Redraw this guy. And by the way, just as a review, these electrons here that just kind of are hanging off the oxygen, we did call those unshared pairs of electrons. An unshared pair, and we would say that oxygen, or excuse me, water in this case, has 2 unshared pairs of electrons on that molecule. Now let's get back to the electronegativity. Now, because if we look at the periodic table here, oxygen is located right here on my periodic table, and hydrogen is way over here. I want to put them right there. Hopefully you can see that oxygen has much greater electronegativity. And when it has a greater electronegativity, it's going to attract all the electrons towards it. So even though it's sharing the electrons with hydrogen, oxygen is pulling on those electrons in this direction. It wants them all around it. It kind of doesn't share very nicely, we could say, to give an analogy. And what happens there is we get a slight charge on this end of a water molecule. It's negative because, remember, electrons, they're negative. And we often label that with a delta sign. So we'll say delta negative on that side. And then the hydrogens are left positive because of the proton in their nucleus. So we say the hydrogens are delta positive. So because of this, this molecule has a slight negative charge right here. And it's got slight positive charges there and there. Now, what does that have to do with anything? Well, let's get into it. Let's talk about a couple more definitions before we dive in here. And then we're going to talk about why this is super important in all kinds of things, in chemistry and everyday life. So first off, the definition is a definition called polar. And this is going to be a molecule with a slight charge. So a perfect example of a molecule with a slight charge, or a polar molecule, would be water, as we just talked about. We would say water is polar. It has a slight charge. And then a molecule that is nonpolar is a molecule without a slight charge. Now, a perfect example of a molecule that is nonpolar would be something like diatomic nitrogen. Diatomic nitrogen. Now, what happens in diatomic nitrogen? Nitrogen forms a Lewis structure just like this, with a triple bond in between the two nitrogens, unshared pair of electrons on each nitrogen. And we have a tug-of-war here for electrons. Both of the nitrogens want all 8 electrons around them. So this nitrogen here will pull in this direction, and it's going to pull in this direction. This nitrogen here is going to pull in this direction, but they have equal electronegativities, and if there's equal electronegativities, there's no way they can actually, nobody's going to win, we should say. So there's no overall charge on this molecule, and that holds true with all of our diatomics. And diatomics are those 7 molecules that pair up to form an octet. And it starts with nitrogen, and then we have oxygen, fluorine, chlorine, bromine, and iodine, and that's 1, 2, 3, 4, 5, 6. And then, of course, we have good old hydrogen as well. Those are our 7 diatomic molecules that like to pair up to form an octet. It also happens, nonpolar also happens in molecules that have certain shapes, and we'll get into that later. Let's talk about one more idea called hydrogen bonding, and that'll be the last idea that we talk about today. And here's another definition for us that we need to take care of. Hydrogen bonding. We also sometimes call it H bonding. Hydrogen bonding. This is when a hydrogen, this is really important, it's got to be a hydrogen directly bonded to a very electronegative atom. Now, the 3 most electronegative atoms are nitrogen, oxygen, and fluorine. So we have to have a hydrogen directly bonded to nitrogen or oxygen or to fluorine to get a hydrogen bonding occurring. And what happens is then we get an intermolecular force because hydrogen, it's so electron deficient, becomes attracted to another molecule that is nearby. So let's give the example of water again, because that's really our unit of study for this next couple weeks. And here's our water molecule. Now, as we can see here, we do definitely have hydrogen being directly bonded to an oxygen. It's bonded directly to NO or F. Now, as we said before, that's going to make the oxygen delta negative. It's going to make the hydrogen delta positive. We have a polar molecule. Now, in this case, hydrogen is sort of deficient in electrons. It's slightly positive. So hydrogen becomes attracted, and we're gonna illustrate this force of attraction just with some dots, to another water molecule, just like this. So hydrogen becomes attracted to another water molecule, and then that water molecule becomes attracted to another water molecule. And you get all these other forces of attraction occurring. So when one water molecule is attracted to another water molecule, which is attracted to another water molecule, we get all kinds of interesting things happen, like surface tension, which we'll talk about in our next video. It's why water forms sort of a skin, as we saw today in class. Now let's give you a couple of non-examples of hydrogen bonding when hydrogen is not directly bonded to N, O, or F. And so let's say we have the molecule methane. This is the Lewis structure for methane, which is CH4. Now, in this case, we do have hydrogen present. It is bonded to another nonmetal. We have covalent bonding occurring. But what we see here is hydrogen is not directly bonded to it's not directly bonded to N, O, or F. Okay, so that's today's video, and just to summarize really quickly, we have these polar bonds or polar molecules that have slight charges. We have nonpolar molecules that don't have charges, and when we do have slight charges in polar molecules, we can have a force of attraction called hydrogen bonding occurring when hydrogen is bonded to N, O, or F. And that's tonight's video.